Hello everyone, I'm Yuguang from EE department, and now I'm presenting to you my class project of the graphical model class, which is an efficient inference algorithm in solving graphs with continuous potentials. Specifically, I'm going to work on the non-parametric Lie propagation. Alright, so let's first take a look at this Lie propagation. So the BP is used to calculate the marginal probability of each node and each edge given a graph. So it is achieved by this two-step procedure: collect evidence and distribute evidence. So basically what we do is we randomly choose a node, use it at the root, and we'll send the message, start from all the leaf nodes and go up to the root until this root node x1 and receive all the message from all the nodes, and then it will start to distribute evidence back to this leaf nodes. So during this process, we'll guarantee that each node it will receive the messages or receive the messages from all the rest of the nodes for only once, so that we can use this information to calculate the join to Gaussian probability. Alright, so let's say I want to calculate the message which is sent from x3 to x1. So I'll use this equation, and we'll first collect the message from this nodes other than x1 and calculate the product of these messages, and I'll use this to multiply the edge potential from x3 to x1. So use this equation to eventually figure out the message. So if you take a look at this, it's actually the product of different edge potentials and node potential. These messages are actually also composed of that. It's like recursively. So if all those potentials they are discrete, then what we'll have in the message they are discrete, and this problem is very easy to calculate. However, in a lot of applications, like those applications in vision area, the probability are modeled by continuous distribution. So then we will have the continuous potentials. So somebody will say, why don't we use discretization to first discretize those continuous distribution and take care of this using a discrete random variable, those kind of technique? The answer is yes, you could do that in one-dimensional case. However, if the node it have 3-4 dimensions, it's hard to finish this discretization process because we have taken too many samples. So in order to accurately calculate each messages, someone they proposed another method called Gaussian Lie propagation. Use a Gaussian family. So what they assume is the node potentials and the edge potentials are Gaussian mixtures, which are the weighted summation of Gaussian functions, and they plug these two equations into the message propagation message passing process and calculate the message and finish the process. So all the processes are done analytically. The good thing to support this process is because the product of Gaussian function is still Gaussian, so the product of Gaussian mixture are still Gaussian mixture. So if we have all the nodes potential they are Gaussian mixture, then what we will have is all the messages they are also Gaussian mixtures. And by using the equation below, we could calculate those Gaussian mixtures. We could calculate the product of Gaussian functions very easily. But here comes a problem. If we have the input mixture, and each mixture they're composed of m Gaussian components, so you can think like different terms, which each terms are summation of Gaussians. When they multiply each other together, what we will have in the product term is m power d Gaussian components. This is it's still a mixture, but it has so many Gaussian components. If we have dozens of nodes and each nodes have 4 or 5 Gaussian mixtures, then the product, then the messages and the final node bleeds, they will become too much complicated, take too much computer memory, and will take too much time to calculate each of those components. So in this class project, I'm going to use a method to efficiently compute the message with continuous random variable while maintaining the accuracy. To do this, I'll use this method, non-parametric bleed propagation, to figure out this problem. And it's actually have a lot of similarity between MBP and the Gaussian bleed propagation. Like I said, this analytical method, right? So in MBP, they will still assume that the potential function are weighted Gaussian mixture. However, when they calculate the product of Gaussian mixture, they will not use the analytical method. What they will do is to use Jeep sampler to sample from the product density. Jeep sampling and the Monte Carlo methods, they follow a certain process, so they can figure out the sample which have the same distribution as the product density function. And from the product density, we will use the kernel density estimation to model the distribution of the sample and rebuild the analytical function of the new messages, which are still Gaussian mixture. Alright, so I mentioned about Jeep sampling. So Jeep sampling is a Monte Carlo method. So let's start from a very basic case, which is discrete case that the A have few states, and each state they have certain probability, and so this is a potential of the edge. So we will first sample the A, and we know the states of the A, then we can use this conditional probability to sample the B. So we use this process, so on and so forth. Then we have a set of sample which is A, B, C, and D, and repeat this process for a certain amount of times. Then that's one sample, and that's a set of sample, and this sample, it will have the distribution of this system. So we follow the same process. We could use the same idea of Jeep sampling in taking the product of a Gaussian mixture. So here is a Gaussian mixture. We will first sample a value from the node equation, and then we'll based on this, we'll sample the xy, and we will sample all those terms which are in the multiplication here, which are in the multiplication process, and eventually we have sample distribution according to the new Gaussian mixture product. So given this samples, we will use kernel density estimation to estimate the distribution function of the samples. So this is a histogram, so you can see that the result is actually composed of different kernels which are Gaussian distributed. We will use the rule of thumb heuristic to figure out the bandwidth, and we'll use the sample point as the kernel centers, so that we will figure out a new expression for for the result distribution. The MBP actually is quite widely used in computer vision area, and it has its application in articulated body tracking and hand tracking. By using this method, when I read the paper, I all find that this method accelerate the processing speed quite a lot, so they allow them to have higher processing rate to process the frame from the pictures. And I have my chance to implement the MBP. So what I did is I coded MBP and I coded Gaussian bleed propagation, which is an analytical method, and I compared the efficiency and the accuracy of the both methods, because the Gaussian bleed propagation, this analytical method, it actually gives the exact result. So you can see that the MBP it can handle the problem with 15 nodes. Each node have 4 Gaussian components, but the Gaussian BP it cannot. Even though the MBP is it's slower than Gaussian bleed propagation in solving a simple graph, but it have a lot of potential in solving the graphs with complex cases. In terms of the accuracy, my MBP method actually gave the average error on this graph is 6.7%, which is which have the result quite close to the exact result. But my MBP method is not stable when the input has 10 or 15 nodes, because this kernel density estimation function I use need a lot of parameters, and I'm still trying to figure out how it changed the result. So the kernel density estimation cannot currently give a fairly good prediction approximation on the density samples on the samples I have. So that's probably is gonna be a direction I'm going to work on in the future work. So that's roughly about my class project. Thank you, everyone.